Okay, in our next video for Chapter 9, we're going to talk about how to now use concentration of molarity as a conversion factor in a word problem. So you can for sure bet 100% there will be a problem like this on the exam. And similar to how we did back in Chapter 6 with like molar mass and mole to mole ratios, I'm going to give you a diagram that shows you step by step how to solve these problems. So we're going to just introduce this concept by working this initial problem, which is just a two-step problem, but then down here you'll learn how to work the full three-step problem. When we say using molarity as a conversion factor, let me explain one thing. How do we use it as a conversion factor? Well, what is molarity? I'm going to actually use the bottom portion of this slide up above. We know molarity is moles of solute per liter of solution. So molarity is moles per liter. So it relates a number of moles to a volume in liters. So just like density relates mass and volume, just like molar mass relates grams to moles. Anytime you're relating two units, you can use it to convert between those two units. Either way, we could go from liters to moles or moles to liters. So look at this problem down here. It says a blood alcohol content of 0.065 mole per liter, meaning moles of alcohol per liter of blood is enough to induce a coma. If the total blood volume of an adult male is 5.6 liters, then how many grams of alcohol are necessary to reach this concentration? So here's the way we go about this problem. We want to know how many grams of alcohol, and we can get grams of alcohol, which is ethanol. So don't be confused when you look at this figure down here. It says ETOH. ETOH is the kind of shorthand notation for ethanol. Ethanol is alcohol, okay? Ethanol is alcohol. So here's how we're going to do this. We are going to start with the volume of blood, 5.6 liters, okay? So 5.6 liters of blood in an adult male. Now it says use molarity as a conversion factor. So here's our molarity. We're going to rewrite molarity over here. It's 0.065 moles of alcohol, which is ETOH. Remember, alcohol is ethanol, per liter of blood. Moles per liter. Blood is the solution. Ethanol is the solute in that solution. So we have 5.6 liters of blood starting out. And now we're going to convert. So for every 1 liter of blood, we're going to convert to moles of ethanol. It's 0.065 moles will induce a coma. Okay. Now how much is that in grams? Because we don't really communicate about alcohol content levels in moles. We communicate that in grams. So now we're going to use the molar mass of ethanol as a conversion factor. So you could look it up really quick. We could just calculate it really quick. Molar mass of ethanol. So we have carbon. We've got 2 of them. So 2 times 12.011 grams is 24.022 grams. And hydrogen, we've got 6 of them times 1 point. I'm going to do 0.01 grams, so that should be 6.06 grams. And oxygen, we've got 1. I'm going to do 16.0 for the grams, so that is just 16.0. And then we add all of that up, so we should have, zoom in, 2 and 8 and 0, and then 46 is what it should be. 46.082, that's grams per 1 mole of alcohol or ethanol. Did I do that right? Double check. Alright, I think that's good. So now we'll just plug in, we want to know how many grams of alcohol, remember, which is ethanol. So now we're going to plug it in so that moles cancel. For every 1 mole of alcohol, you get 46.082 grams of alcohol or ethanol. So now we just do this problem math-wise. We have 5.6 times 0.065. You can divide that by 1 if you want. And then times 46.0 82. And I got, hopefully this is right, 16.77 grams of ethanol, or remember that's blood alcohol. So how much is 16.77 grams? I'm not sure exactly. I don't have. Remember, 1 gram is about the mass of a dollar bill. So about 16 $1 bills. If you put those on a scale, should be about 16, or I guess closer to 17 grams. But anyways, the point here is that right here, we plugged in the molarity. And we rewrote it. It was very, very helpful to rewrite it like this up here so that you can plug it in and see how the units cancel. Okay, next, I want to just introduce this diagram to you, and then we're going to use it in what I consider to be a more complicated problem. So for this balanced equation, we have A and B makes C and D. And anytime you have a balanced reaction, if you are given the volume, because we're dealing with solutions now, remember this whole chapter is on solutions, so if you're given the volume of a solution of substance A, and you want to know what volume of substance B should you put with substance A so that you don't waste anything and you fully make as much product as you could, here's how you work a problem like that. You're going to use molarity to convert from volume in liters to moles of A. Okay? And then once you have moles of A, we use the mole ratio. This is nothing new. You should feel good with that, to go from moles of A to moles of B. And then you're going to use molarity as a conversion factor to convert back to volume, which is going to be liters again, of substance B. This is just like what we did in Chapter 6. Instead of, in Chapter 6, we use molar mass. We would use molar mass to convert from moles to grams, or grams to moles. But here, it's the same concept. We're just using molarity, and instead of going from grams to moles, we're going from liters to moles, because we're talking about solutions, and again, solutions are liquid, so we have to communicate in terms of volume. So this is what we're about to do in the problem we're going to work. There's 2 problems down here. I'm going to choose the second problem to work. Why? Because I really don't like the way this problem is set up. Instead of having you do what I just said, it does have you convert to mass in the end, or it starts out with a mass instead of a volume. It gives you 500 milligrams of it. It's a great problem. I suggest you try to work it on your own, but I want to work one exactly like this diagram, so I'm going to go with problem 2. All right, which says calcium carbonate reacts with hydrogen chloride, hydrochloric acid, to make calcium chloride, water, and carbon dioxide. So the first thing we need to do is we need to write out, remember, all of these problems start out with a balanced chemical equation. So take a second. I suggest you pause the video. I'm going to turn this thing sideways so I have more space. Maybe you can see it better. I suggest you pause the video and write out this sentence. Okay, calcium carbonate, CaCO3, reacts with hydrogen chloride, HCl, which is hydrochloric acid, to make calcium chloride, which should be CaCl2, water, and CO2. Okay, now we need to balance it. Are we balanced? No, we're not balanced. If I put a 2 here, I think we're now balanced. 1 calcium, 1 calcium, 1 carbon, 1 carbon, 3 oxygens, 3 oxygens, 2 hydrogens, and 2 chlorines. Okay, good. All right, so we're balanced. Now it says how many milliliters. So remember the problem, or the diagram up top, will get you from liters and to liters, but we'll have to have an additional step where we convert to milliliters at the end, of a 0.22 molar, and remember this is moles per liter, solution of calcium carbonate are needed to react completely with 25 milliliters of a 0.5 molar solution of hydrochloric acid. So we have 25 milliliters of hydrochloric acid, and it is 0.5 moles per liter. That's the concentration, 0.5 molar. And then we want to know how many milliliters of calcium carbonate, which is the other reactant, and the concentration is 0.22 moles per liter. So start with 25 milliliters. Remember, we're going to call, sorry, I'm scrolling back and forth. A, we're going to call this substance A, and we're going to call this substance B. The one you're given the volume for is A. The one you're looking for the volume for is B. So look at our diagram. The first thing is we're going to plug in the molarity, go from liters to moles. But we've got to have liters of our solution. Right now we have 25 milliliters of HCl. And so we're going to go from milliliters, 1,000 milliliters to liters in 1 liter. And then we're going to plug in our molarity. That's the next thing. We want to cancel liters and convert to moles of HCl. So for every 1 liter of HCl, we'll get 0.5 moles of HCl. Okay, so I just did the first conversion here. I plugged in, this is where I plugged in the molarity of A. Then we're going to plug in the mole ratio. So far too, we've canceled out milliliters, we've canceled out liters. All right. Now the mole ratio, which is, if we look at the coefficients here, it's 2 to 1. So for every 2 moles of HCl, we'll get 1 mole of CaCO3. And then we're almost there. We converted to moles. Now it says how many milliliters of calcium carbonate. So we can plug in the molarity to convert from moles of calcium carbonate to liters, and then we'll go from liters to milliliters, and we'll be done with our problem. So plug in the molarity here. For every 0.22 moles, I'll get 1 liter of CaCO3, and this is CaCO3. So moles of HCl cancel, moles of calcium carbonate cancel. And then the last step, since it says milliliters, is we'll convert from liters to milliliters. So now we just put all this in our, this is a long problem here, several steps. So start with 25 milliliters, divide by 1,000, multiply by 0.5, divide by 2, divide by 0.22, and times 1,000. And I got 28.41 milliliters of calcium, of that molarity of calcium carbonate would be needed to react with all your hydrochloric acid. Okay, so that concludes this video on how to use molarity in what we